Hello and welcome to today's Atlas visit for this CERN Alumni Second Collisions event. My name is Sascha Mielhase. I'm a senior postdoc at LMU Munich in Germany. I've been at Atlas for about 16 years now and am the outreach coordinator. And with me, we'll have today two guides at the Atlas Cavern down underground. That can introduce themselves now. So let's start with ladies first.
Hi, I'm Elise. I am a PhD student at Duke University. So I just arrived at CERN about 2 months ago, and I'll be here for about a year to work on my PhD research. So I do some data analysis, the searching for new physics, and I also work on data acquisition for the next generation of detectors for the high luminosity Lhc.
And then we also have...
Okay, so my name is Mohammed Al-Horoub. I'm a Palestinian physicist working for the University of Oklahoma. I joined Atlas in 2006 and I worked more than 10 years on topic war physics, and I switched to the W board in last 2 years. Right now I am underground, approximately minus 70 meters. Uh, Minus 70 meters on the sixth floor in front of the big wheel, which is the end cap immune spectrometer. As you see, so we are underground. The detector is huge. It's one, actually, it's the largest detector we have around there. You see, it's one of the four big detectors. It's a general purpose detector, and it's not specialized for one physics phenomena, but we can scan wide range of physics phenomena. Like we can study physics, field physics, supersymmetry. We can look for exotic particles, dark matter, standard model predictions, etc. The detector is huge, as I said. It's around 50 meters in length, 25 meters in diameter, and it weighs 7,000 tons, which is equal to the Eiffel Tower in Paris. It's not homogeneous. It's made from many sub-detectors. We have multi-layer structure, and each sub-detector is responsible, designed to measure one physics quantity. So we have the pixel detector, or let's say we have the tracking system, which is made from three sub-detectors. The pixel detector, which is made from 92 megapixels. We have the semiconductor tracker, and we have the transition radiation tracker. So the tracking system helps us to measure the trajectory of the charged particles, and it's embedded inside the solenoid magnet. We have also two calorimeters designed to measure the energy of particles. We have the electromagnetic calorimeter, which studies or measures the energy of electrons, positons, and photons. And we have also the hadronic calorimeter, which measures the energy of hadrons. Hadrons are composite particles from quarks and gluons. We have also toroid magnets. We have 8 central toroid magnets, and actually Atlas is named after them. Toroidal LC apparatus. They can produce a magnetic field between 2 and 6 Tesla. And the last sub-detector is the muon spectrometer. So as I said before, I am in front of the big wheel, and which is the iconic picture of Atlas. Whenever you Google Atlas, you will see this spectrometer. Okay, so
All right.
we have. Go ahead, Sasha. Sorry.
All right. So maybe just to mention, I mean, now you already got a bit of an overview of the different parts of Atlas and so forth, but the main reason for you being here is also to be able to ask questions. So you can use the alumni platform to get questions to us, to Elise and Mohammed at the experiment, to myself here in the home office. So feel free to post questions. They'll be forwarded to us and we can try to address them. So that's one of the main issues. It can be about the experiment. It can be about the work that we do, the physics program. So feel free to ask anything you want. It will end up sort of in front of us, and we'll try to address as many of the questions as we can. Maybe Mohammed already gave a little bit of an overview of what the different components are. Maybe the two of you can quickly say sort of where in Atlas Underground you are. So where are you, Elise, for example, compared to Mohammed?
Yes, so I am on the second level. So level 0 is the bottom of the cavern, and level 4 corresponds to the beam pipe of the LHC. So I'm slightly below the beam pipe, as you can see. It's a little bit higher there, and so I am on the C side. So in Atlas, there is the A side, there's the barrel, which is B, and then the C side is the other end cap of it, so it's a cylinder. So right now I'm on the C side, Mohammed is on the other side. And so this is the end cap. This is closing off the Atlas detector. And it's the muon spectrometer, as Mohammed just explained.
So now you mentioned you're on the C side and Mohammed's on the A side. Can you maybe say what that actually means, Mohammed?
I remember A side, which is the side closest to the Geneva airport. So C, sorry, that's A. C is the other one, which is toward France, so Saint-Denis. So A, airport. C, I don't know what it means, but I know it's Saint-Denis.
All right, so it's actually quite simple. It's the clock, right? One is clockwise and one is anti-clockwise. So it's the same way as the particles that we have in the LHC. So mostly protons, but also heavy ions that are sort of accelerated in the LHC. There's two beams that go counterclockwise around the ring, and one is going clockwise and one is going counterclockwise. And then that's sort of the definition of A and C. And both Mohammed and Elise are sort of on opposite sides. Talking about the beam pipe and the LHC, maybe Mohammed can actually say a few words about that.
So, yes, I am on the 60th floor, as I said at the beginning, minus 70 from the surface, or 70 meters below the surface. The beam pipe was on the 4th floor, and I think it's minus 80. And it's connected inside A. So you see it. So it's between the end cap. Hello?
I think, yeah, now I think we actually lost Mohammed for a second, but you might have seen sort of the grayish beam pipe that is between these big wheels that both Elise and Mohammed were talking about before, and the other part on the right hand side, and that's actually more or less the plain beam pipe. When the LHC actually starts colliding, that will be covered by a big concrete shielding, essentially protecting the detector from stray radiation that's coming from the beam. We actually got our first question. Maybe we can address that, Elise, the two of us. Can you say anything about the run 3 preparations, how they are going, and when we expect sort of first collisions to happen again?
Yes, so for run 3, Atlas had a lot of work to do. So we installed the first small wheel. So this is what you see is the big wheel. So that's the biggest part of the end cap muon spectrometer, but there's also a small wheel, which is similar but smaller, and it's next to it. And so the plan was to install one on each side. So the A side new small wheel is already installed, and on the C side, it is getting ready to be lowered into the cavern in only a few days. So that's been a lot of work and very good progress. There's just also some routine upgrades. As you can see, some of these detector components on the big wheel are being worked on, and various other smaller upgrades. And I believe the actual first beginning of the run will be in February, and there'll be a few tests before that.
Exactly. So we'll actually have in a couple of days, towards the end of October, there will actually be first tests of the LHC. So for half a month, from mid-October to end October, we'll actually the LHC people will try to do some tests, sort of getting a first sense of the LHC after the long shutdown number 2 that we just sort of have right now. And then, as Elise said, in February or March, we'll try to have first collisions, and then also go towards first collisions that are physics relevant. So Mohammed is back. Maybe we can have a
Hello.
quick second look at the beam pipe that we mentioned before. Now you see it very
So,
nicely in the picture.
as you see, the beam pipe connects right now. So it's it goes through the end cap immune spectrometer and the end cap toroid magnet. So it's the black one. And of course, it continues. There is the center of the detector where the collisions occur. This is the last sub-detector. So this muon spectrometer is, let's say, 25 meters away from the collision point, approximately. And it's on the fourth floor, minus 82 meters from the surface.
Maybe one can actually add that what you can nicely see now in Mohammed's picture is that what you see on the left is actually two big wheels. And one of them will be moved towards the toroid, so the sort of silvery blackish structure that Mohammed just talked about. But it seems to have an issue with the connection. Yeah, so it's actually two
Yeah.
wheels that are now moved together. Now you can actually see quite nicely. So let's have a look at Mohammed again. All right,
Yes.
so
So
you
this
basically
is the
see the
first wheel, the second one, and
exactly.
that
So
you
the
see
left.
the blue. Go ahead, Sergio. Sorry for interrupting.
Okay. So the left one is the outer big wheel, as we call it. So that's going to more or less stay where it is, and the right one in the picture is sort of the one that's going to be moved towards the toroid magnet, closing off the inner barrel part, as we call it. And then here you actually see the blue beam, the sort of concrete structure that is around the beam pipe. Exactly, that is essentially shielding the detectors from stray radiation in the beams. Maybe we can also have a quick look over to Elise, where you can also sort of see the other end of the beam pipe shielding nicely in her picture. Exactly, nicely indicated by the blue color again. All right. Maybe at that point, again, feel free to ask any questions that you like, be it about the physics program as we had, or getting ready for run 3, getting ready for the high luminosity LHC, in fact. So the new small wheel update that Lise was talking about is actually also in sort of preparation for this even sort of even the next step of upgrading the experiment, making it ready for many more collisions happening at the same time, and still being able to sort of analyze all these collisions and all the physics data that we collect in those. Yeah, maybe, as I said, feel free to ask any questions you want. Maybe talking about HLLHC and so forth. Maybe, Elise, you want to talk a little bit, because you mentioned you're sort of working on other upgrades that are relevant for that sort of part of the future.
Sure. So yeah, the high luminosity LHC is a very large scale upgrade of the entire LHC and all of its experiments. So it's right now the plan is for it to start around 2026, and high luminosity means that there's going to be a lot more collisions per time and per space. So all of our detectors are going to have to be upgraded to deal with all these extra collisions. So in Atlas, we're actually replacing the entire tracking detector. So Mohammed mentioned the three sub detectors of the tracking: the pixel, the strips, and the TRT. So all of those are going to be replaced with what's called the ITK, inner tracker, and it's going to be entirely silicon detectors. And so, yes, what I'm doing is I'm working on the chips that are going to be used in the silicon detectors to see if we can read out the data from them at the rate that we need to for the collisions and so forth. But there's also a lot of other work that's being done with the software that's needed, or the mechanics, the cooling, the all the monitoring that's needed. So there's a lot of work going in that direction.
Exactly. And then most of these components that Elise just talked about, they will come in, sort of will be integrated and replacing the old parts in the next long shutdown. So the one that's coming after run 3, which is starting next year. And the new small wheel is sort of one of the cases that is already being installed now these days. But it's also sort of looking forward to a large extent at the LHL, the high luminosity LHC. All right, so Mohammed changed position slightly, so maybe you want to give us a bit. Want to give us a bit of a feeling where you are now, and maybe what we can see now that we didn't see before.
So I'm still on the sixth floor, but I was on one side and I turned around the detector to the other side, so closer to the elevator. Now we see more the end-cap toroid magnet, and perhaps we can see the toroid magnets, the central toroid magnets. So we have 8 central toroid magnets. As I said, they produce a magnetic field between 2 and 6 Tesla. We need the magnetic field to force immune particles to bend when they travel through the detector, because from their curvature we can measure their momentum and their electric charges. Since we have high energy muons, so we need very strong magnets, and they are superconducting magnets. So the cable is made from titanium niobium alloy, and they run at 1.9 Kelvin, so minus 271 degrees centigrade. And to achieve this low temperature, we use superliquid helium. So to magnetic system, we have the solenoid magnet, which surrounds the tracking system, and also we have the toroid magnets. Maybe those are the tubes, the gray with orange strips, the gray tubes with orange strips. Those are again the central toroid magnets. The one in the center is the end cap toroid magnet. We have two. This is the side A. There is another one similar on side C.
All
So
right, so maybe since you
go ahead,
since
sorry.
you talked about the toroids, actually, if we switch over to Elise for a second, you can actually right up in the right top corner, you can sort of see, get an idea of one of these sort of inner toroid magnets. So the silver structure with the orange stripes that you see in Elise's picture, the top right, exactly.
Yeah, right there. Yeah, exactly. And the shape of it is sort of a square oval, and it goes further into the center of the detector. Um,
Exactly, and then basically
yeah,
reaches Muhammad on the other side.
exactly. I guess another thing that I wanted to show here is the hole that the new small wheel is going to go into. So that space right behind me is getting ready to welcome the new small wheel in a few days that will be lowered.
Exactly. And actually, the whole sort of yellow structure that you see there is essentially just support structure. So that's going to be taken out again once the detector is put together. So that's really just so that people can do maintenance and people can reach places like the hole that Elise just described. Maybe it's actually good if we stay a little bit with Elise, because we got another question that connects to the high luminosity LHC that you also talked about, right? What do we expect to detect with the high luminosity LHC? So why even going? Why making the effort? Can you say a few words there?
Yeah, I mean that's a good question. We don't really know what we're going to discover, but the goal is to increase the number of collisions so that we have more statistics. So if there are very rare phenomena that occur at the LHC, we might not have seen them yet because we don't have enough statistics. We haven't observed enough collisions for those rare processes to be seen above the background. So that's one of the goals, is to have more collisions, more statistics, so that those rare events, whether known in the standard model or coming from new physics, things that we don't know about, can stand up better to the background. Another goal that is kind of related to that is that if we're trying to measure processes that we know already, that we've already observed, if we want to measure them more precisely, having more statistics is also helpful. And by having a better precision, we can test the standard model and see how good our predictions are, and if there are some deviations, perhaps that can be due to new physics.
Exactly. Though one has to mention that it all comes at a bit of a price, right? So we talked about before that we have multiple collisions actually. So when these bunches of protons, when they collide inside ATLAS, for example, same way in all the other experiments, then in the moment, at least ATLAS and CMS have, I don't know, about 35 is roughly the average for run 2 collisions happening at the same time. Right, so at the high luminosity LHC, that can easily be a factor 10 more. So we need better detectors that are able to separate all these different collisions, because you still want to be able to say which particles came from which interaction to identify the one that might be the interesting one, as Elise talked about. That might be some new phenomena that happens very extremely rarely. All right, maybe we have another question that goes even further into the future, but still connects back. Maybe Mohammed, you wanna give a few thoughts on what would be Atlas's function in a possible future circular collider?
Oh, this is a difficult question. So there are, first of all, the future colliders, whether they are linear or circular, or let's say the conceptual design of the accelerators or the detectors, will rely heavily on the physics we find at Atlas and CMS. Because now let's say we make discoveries or exclusions and know where to look, and that will influence the design of the new detectors. This is first part. Second part, yes, we have the Atlas. We use it to make discoveries, or let's say understand the particle physics, but also we test the current technology. We push our current technology to the limit. We test the tracking system, the silicon detectors, and by doing that, we learn about the detectors, and that will help us in the future to design new detectors. And of course, training people, training the students. I mean, the students today will be the professors of the future. For example, we will learn new analysis techniques, machine learning, artificial intelligence. Those techniques will we apply? We are applying them right now. Okay, we are learning the techniques, but also in the future we will heavily rely on machine learning to apply. We will apply them on the trigger to trigger events, particle identification, construction, and of course physics analysis. So Atlas is vital. It's the prototype now, and it's the production detector, and it will help us to build the future accelerators, or to choose, and of course to build the detector.
So maybe in slightly other words, one could say that Atlas and all the LHC experiment are doing groundwork for any future circular collider, whichever design it might be in the end, right? But as it will be a new collider, that if built, for example, at CERN, if it ends up being a 100-kilometer ring built at CERN, then the LHC will actually just be sort of a pre-stage to it, and ATLAS won't be part of the actual future circular collider. Right? In the same way as the PS, for example, the proton synchrotron, or the SPS, the super proton synchrotron, all accelerators that sort of were the top of the edge at CERN at some point, they're now essentially pre-stages to the Large Hadron Collider. So they pre-accelerate particles that we can then use in the LHC, in ATLAS, and the other experiments. All right, but please feel free to get questions to us. We'll try to address them. Hopefully, we address the ones that we already got to your satisfaction. Elise actually changed position slightly. So maybe Elise, where are you now? Maybe you can.
Yeah, so I'm at the same level as I was before. I'm at level 2, but I just moved to side A. I was at side C before, so just for a slightly different view. So this is the side that actually has the beam pipe, as you can see behind me. And Mohammed is just a few floors above me on the other side.
Exactly. So if we switch over to Mohammed quickly, he's actually pointing at Elise right now. So you also get a bit of a feeling of the size, right? I'm not sure we actually mentioned that already, but the big wheels that you see on the right on the left in Elise's picture, on the right in Mohammed's picture, they have a diameter of about 25 meters, right? So they almost fill up all of the cavern in terms of height, but it's 25 meters, and you can see Elise nicely down there. Exactly. And then in length, Mohammed sort of indicated that already, right? From the end, from one of the end big wheels to the other side, big wheels, it's about 45 something meters. Just to give you an impression, now you also have, with the Lee standing down there, a bit of an idea of the size, if you haven't had that before. All right, maybe since I think Mohammed has a bit of an odd position, but maybe Lise, can you move the camera up a little bit to see the cavern top ceiling? Yeah. So what is it we see up there?
Yeah, so this is the shaft that the detector parts are brought in through. So most of the parts are built at the surface and then lowered into the cavern and assembled underground, because of course we can't build this big of a detector and then lower it all at once. So this is one of the shafts, and there is another one, and they have a diameter of around I think 15 meters or something like that, and they lead all the way up to the surface.
And you can also see sort of in the shafts, there's a lot of piping and everything. So that already gives you a feeling. So this is basically to pump fresh air in and out. That helps with the general ventilation. It also helps with the cooling. There's also pipes for that. I mean, a lot of the detectors have to be cooled to temperatures below zero, sometimes significantly below. So not just the magnets that Mohammed already, but maybe Mohammed can say a few words about that, about cooling in ATLAS, where it's used and how it's done.
Okay, so the detectors, the sub-detectors should be cooled down because we apply high voltage and they heat up. And I can start from the innermost part of the detector to maybe the muon spectrometer. So the pixel detector is made from 4 concentric layers. The innermost one is cooled by carbon dioxide, and the temperature in principle can go down to minus 80 degrees centigrade. The other layers, the first, second, third one, the second, third, fourth, I mean, sorry, excluding the first one, they are cooled by fluorocarbon C3F8. And temperature depends, sometimes minus 10, sometimes minus 20 or minus 40, depends on the LC intensity and on the high voltage we apply. So during the year, the LC intensity, the number of bunches it change, and according to that we adjust the high voltage, and according to that we have to adjust the cooling temperature. If we have low intensity, we don't have high voltage, maybe we can run at -10. But if high intensity means we need to apply high voltage to suppress the noise, and of course the detector will heat up, and we need cooling power, so we drop the temperature a lot. So that's the pixel detector. The SCT cooled also down, but I don't know exactly the temperature. The TRT runs at room temperature. The first calorimeter, the electromagnetic calorimeter, sometimes we call it liquid argon calorimeter. It runs at minus 183 degrees centigrade. The second one, the hadron calorimeter, honestly, I don't remember its temperature, but I believe it's cooled down. The Muni spectrometer, the one you see, it's at room temperature. We don't cool it down. It's room temperature. It's far away from the collision point, and there is not so much demand. Let's say, I mean, the probability to hit the same detector, the same sensor twice with two consecutive collisions is very low. So it can run really at low temperature, sorry, at room temperature. So it depends how, I mean, the temperature, how cold it is. It depends how far away from the collision point. It depends on the technology. It depends on the voltage we apply.
All right. Maybe since you mentioned sort of the tracking detectors already in a bit of detail, the calorimeters, the different types of calorimeters, any one of you wants to sort of say a few words about sort of the different types of calorimeters that we have and what the main difference is between them?
Go ahead, Mohammed.
So we have two calorimeters. The first one, which comes in the, hello?
Yeah.
I,
Oh,
go,
okay. So then, then I'll
Should
take
I
over
take
first.
over? Or yeah,
Yeah,
go ahead.
please, Elise, please, Elise.
Okay, so the main principle of a calorimeter is that it stops the particles and it measures their energy. So it's made up of layers of one material that slows the particles down. And when they're slowed down, they emit showers of new particles. And then that is alternated with layers that measure these showers. And so then we can make like clusters within the calorimeter to kind of group all the particles that came from the original particle, and we can determine its energy. So the different types of particles, electrons, photons, or on the other hand, hadrons, will interact differently with the materials, and so that's why we have two calorimeters. The inner one is electromagnetic calorimeter, so that one is specialized for electrons and photons, and then the hadronic calorimeter is specialized for protons, neutrons, and other types of hadrons. And so they use different materials. So, like we said, the liquid argon for the electromagnetic calorimeter, and for the hadronic calorimeter, I do not remember the material, but it depends on the properties of the particles that we're trying to measure.
Yeah. So the liquid the hadronic calorimeter actually uses two different systems in Atlas. So especially in the forward regions, it's also a liquid argon based calorimeter. So liquid argon being sort of the active material that Elise talked about, where you measure the particles that are created in these showers. And then you have a heavy, dense metal as the sort of passive material that tries to stop the particles, tries to induce these additional collisions so that the particles lose energy by creating new ones. And then we also have a so-called tile calorimeter that uses scintillator tiles as the active medium. So when charged particles go through, they emit light, and that is sort of collected, and that gives you an idea of how many particles have been created with what energies and so forth. All right.
Hello, can you hear me?
Yes, we can hear you again,
Okay, good,
Mohammed.
great.
Maybe so now we talked about tracking detectors a little bit. We talked about calorimeters a little bit. You've mentioned already the muon detectors that we see there. You actually, just behind you, before you sort of moved the camera, there was sort of other parts of the muon detector visible, or actually on the other side, but never mind. uh, exactly, there. Oh, wait.
No, 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 I will be as close as possible. Yes.
All right, okay, then maybe you can talk a little bit about the different kinds of detectors. You have a nice example
Okay,
just in front
so
of you
it's
there.
very simple technology, the beam spectrometer. We have drift tubes made from aluminum. It's around maybe 2 centimeters in diameter. There is a mixture inside the gas. I mean, carbon dioxide, maybe argon, mixed with argon. So it's very basic principle. So when particles here, the muons, the heavy brothers of electrons, go through the gas, they will ionize it, and electrons will drift to the anodes. So there are in each one there is very thin wire in the center. So when the gas is activated or ionized and electrons drift to the anode, so we'll have electric pulse in in the tube. And we know the position of the tube precisely. So we know that the particle passes through this one. We have 1, 2, 3, 4, 5, 6, etc. So we have 6 points in space. So we can make the fifth. Of course, we have two wheels, and we have the information from the tracking detector, the inner detector. So we can have the full trajectory of the muon particle. And if we know the magnetic field, we can calculate the momentum of the muon particle and its electric charge. Here, the electric charge will be positive or negative. That's it. So very simple technology. As you see, we have many tubes. So like we know whether it comes through this tube or this tube. The accuracy is not so great. It's plus minus, let's say, 1 centimeter. But you know that we are far away from the collision point, and when we divide, let's say, the accuracy by the distance from the collision point, we can get very precise angular measurement.
All right. Then maybe moving a little bit away, topic-wise, discussion-wise, from the detectors. Or actually, I think Lilise is having another nice sort of view of one. So let's have another quick look at what Elise is has in focus now.
Yeah, so we mentioned the different types of muon spectrometers. So this is one type. That's this is the barrel detector. So the big wheels are the end cap detectors, and this is the barrel part of it. So it's yeah, there are several that go around the center of the detector, and this is just one of them that you see behind me.
So that's actually quite nice that you're showing that. Because you see nicely the LMU logo on it. So that has actually been built at my institute. So thanks for doing that. No, but staying with you, but moving a little bit away topic wise, as I said, from the detector. Another question: what is it that you're doing actually in Atlas right now, other than the ITK upgrade, for example?
Yeah, so I work on an analysis that is searching for a heavy resonance, so a particle like the Z boson, but heavier, so we call it a Z prime. And this would be a Z prime that specifically is produced and decays with and to top quarks. So we have a Z prime that's produced at the same time as two top quarks and decays back to two top quarks. So we have a four top quark final state. And this is a very interesting final state because we have a lot going on. It's very busy. We have a lot of jets of particles. And so it's very interesting to try to reconstruct that event and detect that resonance. So the goal is to kind of see if we can see a peak in the resonance, in the mass of the reconstructed mass of that resonance. And so we try to optimize that reconstruction and then our statistical analysis to come up with an answer for whether we see this resonance. And so we just made this public for a conference recently, but we're still working on some further optimizations and planning on another iteration of this in the future. So that's just one example that I'm working on.
All right, then let's just hand this question over to Mohammed as well. So what are you working on right now, Mohammed?
So I
Physics
am
analysis
involved in
wise.
physics analysis. So I am involved in multiple analyses. The first one is the simultaneous production of the 3W boson. Actually, Atlas Collaboration announced the discovery of this process 2 months ago. We are finalizing the analysis to publish it. To publish it in peer review journal. I am also involved in a search for the production of 2W bosons plus photon. And another analysis is the production of the topic work in association with Z boson. So three analyses, one of them is almost done. I do also service work, so I work with the database of the pixel detector. So I am managing the condition database and also coordinating Atlas virtual visits.
All
So
right, then
three analyses plus the service.
maybe just to maybe in if you can in 1-2 sentences, why is, for example, the three W's produced at the same time? Why is that so interesting?
So it's predicted by the standard model of particle physics. It's a rare phenomenon. Uh, to make discoveries or to falsify the theory, we have to look for rare phenomena. Because if it's not rare, people would have seen it long time ago if there is a deviation. So this is one way to falsify well-known theories. Look at rare predictions. Of course, when we look at it, discover it, measure the production rate, we compare what we see to the prediction. Either we have a discrepancy and we say the theory is inefficient, sufficient to describe particle physics, or yes, the theory passed another falsification test. It's interesting because also we can measure one of the fundamental parameters in the standard model. We call it the quartic gauge coupling. So standard model has many free parameters. They should be fixed by experiments. And the simultaneous production of 3W boson allow us to fix one of those parameters. And of course, measuring this parameter, fixing it, might give us a hint if there is a physics beyond the standard model.
All right. All right, then now we had or you had sort of an idea of sort of a few sort of very distinct analyses that we do. As Mohammed introduced at the very beginning, Atlas is actually a so-called multi-purpose experiment, the same way as CMS is. And we do hundreds of different sort of analyses, measurements, precision measurements of the standard model to sort of confirm or sort of falsify or find deviations. Also, deviations might be signs of new physics. And there's lots of searches, as both Elise and Mohammed sort of described, where you search for new phenomena. So especially in Elise's case, you actually search for new particles that are not part of the standard model, not part of our current understanding of sort of the world around us, which is basically, in terms of theory, the standard model right now. Talking about that we have sort of hundreds of different analyses, maybe we can also say a few words about the collaboration, right? So it's we're just 3 out of thousands. So Elise, do you want to say a few words about the collaboration itself?
Sure. So Atlas has about 5,000 members, but there's a wide variety of roles that people can have. So are those who work on physics analyses. There are also some engineers, some administrators, and a lot of students, of course. Some people work on multiple different aspects. And so, yeah, a variety of roles. And then within this collaboration, because it's so large, we need to have some sort of structure. So there are multiple groups within the collaboration, and then some subgroups within those groups. And then there's a few different levels of that until you get to a team that works on a given project. And so then that team responds to their subgroup and then their group, especially when they try to get their project approved, either if it's an analysis towards publication or if it's a hardware project towards implementation. And so there's the work, the everyday work is done with your project's team, but then there's still a lot of collaboration and communication that's being done with the group and the subgroup, and then there's also a management team that oversees everything, that communicates with the other experiments and with CERN itself. And then we also have some specific groups like the outreach group. And so we have people from a variety of different fields within Atlas who come together to promote what we do. And yes, there are a lot of different things that are being done within Atlas.
All right. Did we actually mention, right? It's about 5,000 people in Atlas.
Yes.
In total.
Yes, I mentioned that. Yeah.
Okay. And that includes all kinds of sort of professions at all different levels. Exactly. All right. Maybe just to mention again, feel free to ask any questions, whatever it might be. We have about 10-12 minutes left of the event. So if you want to get your questions answered by either Mohammed, Elise, or myself, then please put them in the system, and we'll try to address them. Yeah, maybe in the meantime. Oh, I think we just lost Mohammed again. I was going to address my next question to him. Anyway, yeah. Now I got out of tune. Right, Elise. I mean, you talked about the collaboration. You talked about your work. What was your sort of, since it's an alumni event, right? What was your path to coming to CERN, maybe? And
sure. So I did my undergraduate studies in the U.S. in Minnesota, and so I was in a small university that didn't have a lot of research opportunities. So I did a summer research experience for undergraduates program with Duke University. So I spent part of the summer at Duke and then the other part of the summer at CERN, and that was a really great experience for me. I was introduced to particle physics. I didn't know almost anything about it beforehand, and it was really very eye-opening and made me want to continue research in that field. So I came to Duke for graduate school, and now I'm working with the same professor that I was working with during my summer program. So that was just a really great experience for me. And so now I'm a couple years into my PhD, and yeah, like I said before, I arrived at CERN about 2 months ago, and I'll be here for about a year to work on the various things that I mentioned before.
All right, having Mohammed back, maybe I just wanted to, another question that also often comes up is, what's your favorite part of the Atlas detector? The one that you like the most, and the one that you like showing the most, and maybe you can actually show it if you can.
Uh, you ask me.
Mohammed, yeah, yeah, yes, I'm asking you.
I
Yeah.
mean, the only sub-detector we can show these days is the moon spectrometer. Uh, Actually, I love all sub-detectors because we need all of them to make a measurement. I mean, I can't say, okay, I need the muon spectrometer and leave the pixel. It doesn't work like that. So we need the tracking, we need the muon, we need the magnet, we need we need the calorimeters. So any measurement will rely on all these sub-detectors, and we need the best sensitivity possible.
All right, that's a very political. That's a very political correct answer. All of them are the best. That's good. Uh, but sometimes, maybe just by the fact of what you worked on, you have a slight preference here or there. I mean, at least you said you're working on the upgrade of the tracker, so that's actually a detector that we don't have yet. But maybe you have one that you like, that you like the most, or that is most interesting for you.
Actually, I was just thinking, not really a sub-detector, but I really like seeing the beam pipe. I think that's really cool. And in, the first few times I came here, it wasn't in yet. So it was kind of interesting to see it that it had been put in the meantime. And it's just really amazing to me that these the protons that are the beginning of all this work, they just start in this tiny little tube, and then we have these massive detectors to measure the products of that. So I like seeing the beam pipe.
All right, that's very nice. It's not actually a part per se of the Atlas
Right,
experiment,
right.
but it's still it's still very important. Though actually, the first layer of tracking detectors that you talked about before is actually glued right onto the beam pipe, essentially. Obviously, in the center part, not where we're seeing the beam pipe right now. Um, but talking about the beam pipe, maybe there's actually another interesting thing about the LHC that maybe also don't everybody knows, in terms of the level of the beam pipe. Maybe Mohammed, you know what I'm talking about. You want to say a few words?
Yeah, so the LC is not flat, so it's built a little bit. So I think when we go to the center of Atlas, it's a little bit higher, or the detector is bent and the beam pipe is there's like a couple of degrees with incline. So let's say the beam will climb a little bit, not going in flat direction. Is that what you mean,
Yeah,
Sasha?
yeah, yeah, yeah. So there's actually
Yeah,
here we
but
have a
it's very
question.
hard. It's very hard to see it now because usually we see it when we look at the scaffold. But
But maybe
since the scaffold
because
is removed,
there's actually a question coming up from that. Why is it tilted? I mean, why is the LHC sort of not completely horizontal in the ground?
yeah, the LHC is very heavy, and to when they dig the tunnel, they wanted solid ground. Otherwise, the LHC will sink. And so that's dictated by the ground. So solid ground, and then it was inclined a little bit.
Yeah, so they basically matched sort of a certain layer of rock that they can put it into, so that it doesn't shear, and you don't have any movements that might sort of interfere with the running of the LHC. All right, so we have about 5 minutes left for your questions if you feel like asking some more. that we can still address. Otherwise, I mean, you can sort of obviously enjoy the view that Mohammed and Elise are giving you. Um, so maybe we can actually see Elise again nicely in Mohammed's picture. So if we want to tune to that again, and then Mohammed is also nicely showing exactly. Now he's showing Elise exactly. Maybe you can also say a few words about the electronics that we see on the. Whoops! Now he's turning on the big wheels. I meant. Yeah, exactly.
Yeah, so maybe I can say a little bit. So we have 40 million collisions per second, 40 million bunch crossing, which means every 25 nanoseconds we have a collision. Each collision, if we record it, occupies around 1 megabyte on the hard disk, which means terabytes per second. We don't have the computational power nor the storage capacity to record all that amount of data. So we need to filter the event. And actually, we do that through the trigger system. We have two levels, level 1 and level 2. Level 1 can reduce the rate from 40 million to 100,000 collisions. Then the 100,000 collisions will be transferred to the cluster, the computer cluster above the surface. And then we run our construction algorithms and reduce the rate to 1,000 collisions. But now I speak about the first level, which is the hardware level. It's done by the detector itself. We have the detector is divided into regions of interest. If some regions of the detector are activated by a collision, it means that we might have candidates. We have candidates for interesting particles, and that is enough to trigger the event. Keep it. If we don't activate any region of interest, it means we don't have candidates for interesting particles, and we delete the event. Of course, that's done by electronics, and here we have the electronics which collects the data, and let's say immune spectrometer. And if we have information here, this is one of the regions of interest. We can send, or those electronics send signal to other sub-detectors to transfer the data to the cluster. And it's very important, I mean, the timing, because particles here arrive late. Many collisions occur in the center before the muons of the first collision arrive here. So timing is important to associate particles to or let's say to their frozen collisions or their bunch crossing. That's what I want to say. So they are important to read the data, to trigger the event, inform our sub-detectors, and also for timing.
Mhm. And maybe just to add sort of a number to that. That is also quite interesting. So basically, we're throwing away more than 99.99999% of the data that is not sort of relevant for the physics. So these algorithms that are running on these electronics and also on computers close to the experiment, they have to pick out these very few interesting events that we're actually able to write out on a storage system and then analyze in the analysis, for example, that Elise and Mohammed talked about earlier. So we actually have a question concerning sort of the universities. So the question is, what are the different universities involved in the various sub-detectors of Atlas? I don't know if any one of you has a number. Okay, then I think what I remember. I mean, one has to say there's lots of universities. So Atlas has member universities, member institutions. It's not always universities. Sometimes it's also national labs and things from 41 countries all around the world, and it's about 180 institutes from these 41 countries that work on all of Atlas. And then all of these institutes are involved in different, sometimes also more than one subsystems. And that means building it, keeping it running, writing software, anything you need to run to run the experiment. all these institutes are involved in. But it's hard to say now explicitly which ones are in which one. But it's a lot, as you heard. All right, I think that actually slowly brings us to an end. We have about 30 seconds left. So I think thank you very much, Elise and Mohammed, for being in the cabin, for giving us this nice view. And okay, we have a few seconds more. I've just been told. All right. But anyway, thanks a lot for being down there, for showing us the experiment. Thanks everyone for the questions, for sending them in. I hope we could address all of them, all the questions you had, to your satisfaction. Yeah. Maybe Elise, Mohammed, do you want to say a few sort of wrap up words from your side?
Um, I can tell the people that we organize virtual visits, and first of all, I invite them to come to CERN, and if they can't, we can organize virtual visits from the cavern, and we can speak in detail about the detector, about physics, and we can send the students, we can send the senior postdoctors, the professors. We can also speak in English, or we will find the speakers in multiple languages like German, Spanish, French, other languages.
Elise?
Yeah, I don't really have anything to add. I just thank you everyone for connecting, and I hope you enjoyed it.
Then maybe as a few last words from my side. Obviously, as Muhammad said, there's multiple ways of getting in touch with us. You can visit our webpage, atlas.cern, find out more. You also find the virtual visits. If you want to have another tour, ask more detailed question, then feel free to do so. You'll find all the information there, or on our social media channels. We're on Twitter, on Instagram, on TikTok even, and YouTube. So also from my side, we hope that you really enjoyed the tour. And yeah, I think that's at this point sort of a wrap from our side. So thanks again, Elise. Thanks again, Mohammed. Thanks again, everyone, for joining today. And then enjoy your CERN Alumni event, the rest of that to come.